lesson for 5-1, nth roots, radicals, and rational exponents. So our essential question for this section is, how are exponents and radicals used to represent roots of real numbers? So up at the top, some information. An nth root of a number c is x, such that x to the n power is equal to c. An nth root can be denoted by a radical symbol with an index of n. So for example, the nth root of c. C is called the radicand. So whatever's inside of that radical is what we call the radicand. Part A here of example 1 says, what are all the real cube roots of 125? Well, a cube root is where we change the number inside that square root to a 3. Typically, with a square root, you don't see the number, it's an understood 2. So by having a cube root, or if you have any other number there, that means that you are taking roots that are not square roots. So we might be taking cube roots and fourth roots and fifth roots, and I will probably in another video go over what some of those roots are so that you can get those copied down. So cube root of 125, we want to know what number times itself 3 times is going to give you 125. So you're basically solving that equation for x. Well, the cube root of 125 is 5. Just positive 5. There are no other possibilities here because a negative 5 times itself 3 times would actually give you a negative 125. If we were to go through and factor this to solve, it does give us a difference of cubes that would factor into x minus 5, x squared plus 5x plus 25, and this trinomial does not factor. That's actually not even a real solution. So that's why we only get the one solution here, and that is 5. Part B, what are all the real fourth roots of 16? So I want to know what number raised to the 4th power is going to give me 16. This one I'm going to look at through factoring, because if you don't think about it this way, there's a very good chance you're actually going to miss some of the answers. So if I move the 16 over to the left, I have x to the 4th minus 16, which factors into x squared plus 4 and x squared minus 4, because that's a difference of squares. And then I have an additional difference of squares. X squared plus 4, I'm not going to factor that further, because the only way to factor that would be to get imaginary solutions, and it says real. So real means that we are excluding anything that has an I in it. So the x squared minus 4 factors into x plus 2, x minus 2. X squared minus or plus 4 is not real. However, x plus 2 gives me negative 2, and x minus 2 gives me positive 2. So the only real roots that this would have are negative and positive 2. Example 2, we're going to look at some exponents and look at the meanings of them to kind of derive some other way to think about radicals. So we have in part A, what is the meaning of the exponent in the expression 16 to the 1/4 power? And to really think about how this is important or why it applies, you want to think about 16 and the different ways you can rewrite 16. Well, 16 is the same thing as 4 squared. 16 is also the same thing as 2 to the 4th power. And it's actually that second equality that I'm going to use to make a point in this problem. So I can rewrite the 16 as 2 to the 4th power. One of your rules of exponents when you have a power to a power is you multiply exponents. So this is the same thing as 2 to the 4 over 4 power, because 4 times a fourth is 4 over 4. 4 over 4 reduces to 1, so this is really just 2 to the first power, which is 2. Well, if you think about 16 and you think about 2, and the fact here we said that 2 to the fourth is 16, if I were to take the fourth root of each side of the equation, I'm going to end up with 2. So really, this 1/4 power is the same thing as taking a fourth root of whatever number you have. Let's look at part B to reinforce this. What's the meaning of the exponent in the expression 27 to the 2/3 power? Well, 27 we can rewrite as 3 to the third. Using the same thing that I did in the previous question, I'm going to multiply exponents. And 3 times 2/3, well, that's 6/3, which is 3 squared, which is just 9. So it's like taking the cube root of the 27 and getting a 3 and then squaring it. And that is very important whenever you have rational exponents. This is your concept here. If we interpret, it says interpreting fractional exponents. Your index of your radical is equivalent to the denominator of a fractional exponent. So if you have an exponent that is a fraction, whatever is in the bottom of that fraction, that is the radical of the index of your radical. So if you have something that has a denominator of 2, that's a square root. Denominator of 3 is a cube root. Denominator of 4 is a fourth root. You may see 5 or 6. 5 would be fifth root, 6 is sixth root. Once you get beyond fourth root, your numbers expand very, very quickly. So for example, we already have the squares and the cubes. Obviously 1 to the fourth is still 1. 2 to the fourth is 16. 3 to the fourth is 81. 4 to the fourth, I'm not even sure what that is offhand. It's going to be 16 times 16. So I think we're looking at 260 or 256. 5 to the fourth power is 625, and it's really rare that you're going to see something that's bigger than 625. And then if we look at the fifth powers, 2 to the fifth power is 32. 3 to the fifth power, I don't think that's 3 something, I think it's 2 something, hold on. It's 243. 4 to the fifth power, you may see that one, it's very unlikely though. That jumps the whole way up to 1024. And then sixth powers, you'll see 1, you'll see 2. 3 to the sixth power is 729. So you may see that one. It's very unlikely you'll see anything different than what we have up here. And you can always check by trying to take that radical on your calculator. So you can see here, it doesn't matter if you have a 1 or if there's a number in the top, but you can rewrite terms. If you have c to the m over n power, that's the nth root of c, and then the whole thing to the m power. Or you can say it's the nth root of c to the m, and you can put the m inside. So it doesn't matter if you put the m inside with the c or outside. Typically, it just depends on how your problem is set up and what makes the most sense. And you'll see that in our next example. So we're going to evaluate a couple of expressions. The last one we do have to use a calculator for, and I'll bring up the calculator to show you how to type that in. It should work the same on Desmos. Luckily, when you have these, I know we aren't switching back and forth between the radical format and this format, but it works the same way. It's much easier to evaluate with these fractional exponents than it is trying to type the radicals in most cases. So 32 to the 3/5 power, we can think of that as the fifth root of 32 cubed, or the fifth root of 32, and then the result raised to the third power. Well, The second one is going to be a whole lot easier to work with because I don't know what 32 to the third power is right offhand, but I do know the fifth root of 32, according to what we wrote down in the previous slide, is 2. So this is the same thing as 2 then to the third power, which is 8. So 32 to the 3/5 power is 8. The middle one, very similar. We do have a negative exponent, so I do have to rewrite that. Negative exponent means you flip your term, so this 27 to the 2/3 power moves to the denominator, and then I can rewrite this. And it's going to be easier to think of this as the cube root of 27 and then the result squared, rather than squaring the 27 and taking the cube root. So the cube root of 27 and then the result squared. Well, the cube root of 27 is 3. 3 squared is 9, so my answer here is 1/9. If we look at the calculator for the last one, I could rewrite this if I wanted to. However, I don't know what the fourth root of 50 is, nor do I know what 50 cubed is, and that's where your calculator comes in. So let's find our calculator here. So we're going to type in the 50. Then I'm going to use the caret key. If you have an older calculator that just puts in a caret symbol, which looks like a triangle without a base, you would have to open up a parenthesis to do this fraction, but you can see mine kicks it up so that it's all in that exponent, so then I can type in my 3 divided by 4. You can hit the right arrow if you want to jump back down, hit enter, and if we round this, it's going to be about 18.80. I am going to use my approximately equal to equal sign so we can see how that looks. The next one is a very interesting connection, and I'm not actually going to work through this because this is something you just basically plug in and use your calculator for. So we have the fajita scale of a tornado, and you have this equation up here. Your fajita rating F equals the cube root of W over 14.1, the quantity squared, and then the whole thing minus 2. So you can rewrite this. It's W over 14.1 to the 2/3 power, and then minus 2. It might be easier to plug that into a calculator if you use the fractional exponent instead of the radical. And it says, what is the fajita rating of a tornado with estimated wind speeds of 100 miles per hour? So you plug in the 100, you use a calculator, and you actually get the decimal 1.69. Well, the interesting thing about the fajita scale is this is a round down scale. So even though 1.69 is closer to 2 than it is to 1, it's still considered an F1 tornado because you have to actually reach the next threshold to be considered up at the next level. So I just thought that was kind of an interesting connection there with the fractional exponents and the different radicals that we have. The next thing we're going to look at is simplifying nth roots. So a lot of these ones are going to simplify completely, and when we get into 5.2, we're going to have some things that are not going to simplify completely. So for today, you really shouldn't have anything left in the radical. Everything should go completely. So part A, we have the fifth root of 32 m to the 15th power. So we would take the fifth root, or you could think of this as a fractional exponent. We could think of this as 32 m to the 15th to the 1/5 power, and then I can distribute that exponent. So it's 32 to the 1/5 m to the 15/5. Well, 32 to the 1/5, the fifth root of 32 is 2. M, the 15 over 5 reduces to 3. So this is 2m to the 3rd power. Really, whatever your radical index is, if you have any variables inside of your radical sign, You're just dividing those exponents by whatever your index is on the outside. Now up at the top, you should see I have written even out, even in, and odd answer. There are times when you have to use absolute value to force something to be positive that might not always be positive. And this is how I was taught this. I know there are some books that will leave off the even out, and they'll just say, well, if you have an even exponent inside and you get an odd exponent answer, you need absolute value. But what I was always taught is if you were taking, say, in this case, the fourth root of something that is to an even power and you get an odd answer, you need absolute value. And you'll see what I mean once we go through this. So I'm going to divide the 4 into the 20, and I get x to the 5th power. I'm going to divide the 4 into the 8, and I get y to the 2nd power. Now, if x would happen to equal a negative number, x to the 20th power would give me an even, but if I look at x to the 5th power, that would be a negative. And you guys know it's not possible in real numbers to take an even root and get a positive answer, or to get a negative answer. So because the x has a 5 as an exponent, that would be the odd answer. We need absolute value around it. Y is good because its answer is already even. So even index outside, that's the 4. Even index inside, that would be the 20. And an odd answer, that's the 5. That's when you need the absolute value. We didn't need to worry about it for part A because I was taking a 5th root. So because I was taking a 5th root and that was an odd exponent or an odd index, I didn't need to worry about it. This is the last example we're going to look at in this section. And we need to solve the equation. So you're going to, in the standard way that we've been solving, you want to isolate the variable term. So I'm going to start off dividing by 2. So I have x to the 5th equals 32. Now I can solve this by taking a 5th root or raising to the 1/5 power. It doesn't really matter which way you go with that. So I can do this. Well, if I'm taking a 5th root, I don't have to put down a plus or minus. You would have to put down a plus or minus if you were doing some type of even index, like a square root or a 4th root. But the 5th root of 32 is only one number, and that's 2. So just to conclude, to solve an equation in the form x to the n equals c, find the nth root of both sides. You can raise it to the 1/n power. I actually took the nth root, but they both work the same way. So it just depends on what you're more comfortable with. These fractional exponents do appear on standardized tests, so don't be surprised if you see it on a PSAT or SAT in the future. That's going to conclude 5-1, nth roots. We will be continuing using radicals throughout the rest of chapter 5. So go back, rewatch this video, let me know if you have any questions.